To derive the directional derivative, we'll need these concepts. So I just listed them out here so you can verify that you're familiar with all of these, which I'm assuming you probably are if you're in multivariable calculus. It's going to be important. We're going to use so we're going to parameterize the surface function, this here, with the variable h, and then we're going to use the chain rule, the multivariable chain rule. So that's kind of where we're going. Um, the idea is that if we have a point on the surface and we want to take a derivative in some miscellaneous direction, well, we need 2 points to specify that direction, and then we could think of a point P and a point Q, and if we want to take the derivative at P, we bring Q infinitely close to P by bringing this distance to 0, and that's the idea of the derivative. The main thing we need to do is to be able to specify the direction, and so the work for that is really just down here on the floor, because all we need is a two-dimensional direction. We don't need 3 dimensions. So if I wanted to go from this point, which is going to be up here on the surface, this is what I really want. But if I know I want the derivative at some xy point here, and then we're going to go some miscellaneous direction this way. So I need 2 points to make that happen. So this point would be x plus a little more, so x plus delta x, and then y plus delta y. We also want a direction vector that allows us to specify the direction we want to go in. So let's make a direction vector that we call u. And so u will be this vector. It's important that to remember we always make this a unit vector because we don't want it to influence anything except direction. And now what we're going to do is we're going to make the vector equation of this line. So that would be the vector xy, because this technically is a vector if we're thinking in terms of vectors. It's obviously not necessarily parallel with this one. And to that vector, we will add a scaled up version of this. So we're going to use h, which is going to be our parametric variable, h times the direction vector. And that accounts for this line here. Now what I want to look at is, well, actually, I think what I'll do here is I'm going to bust this up into the individual equations it represents. So that's going to be x plus h times u1, y plus h times u2, and then let's name these x dependent on h and y dependent on h. And so this is the pair of parametric equations that describes this line. Okay, now let's talk about this distance. I'm going to make the case that this is distance h, and then we're going to take h to 0 using first principles, and that is the concept of our derivative. So this distance would be comprised of an x distance and a y distance. So this is going to be delta x and delta But I want to look at the fact that x plus a little more is exactly what's happening here. So this is effectively delta x, and this is effectively delta y. So what I'm going to do, I want to replace delta x and delta y with those. So delta x is h times u1, and delta y is h times u2. And now this distance, if we use the distance formula, oh, I did want to, let me hold up a second here. I wanted to just point out that this here is our linear equation, which you can always kind of correlate with y equals mx plus b, because this is our fixed point. This would end up being b. This is our input variable, so that would be in place of x. And the slope, the direction vector, is the slope. It's a y ratio compared to an x ratio. So I just wanted to point this out, that the direction vector is really nothing more than the slope of the line in the direction we want to go. Okay, so continuing on with this, we're getting an expression for, I guess we could put parentheses here, but I want to get an expression for this distance. Well, I've done this down below for speed. And so I just substituted here and here. And then just simplification to get to here. And then I factored out the h squared, which ends up being outside. And that just leaves this thing. But you'll notice this is nothing more than the magnitude of the direction vector. And we made sure that that was going to be 1. So it's h times 1, which is h. So this is just h. So this distance here is h. And so now we want to make h 0. We want to bring this point infinitely close to this point. So what we're going to do now is just simply take our points and make a difference quotient out of them by basically thinking of, I can turn this the color I want. Anyway, let's bring the points up to the surface. And that's the idea. So now the stage is set. And now this is going to happen fast. So all we need to do now is just think of this. So if I want to take the derivative in the direction of u of this function, and remember x and y are both dependent on the parametric variable h, well then we can make a difference quotient here where we're going to take h close to 0. And but this is just for this is just kind of like for your conceptualization. But what we're really going to use is the multivariable chain rule. So df dh. So we have these 4 things, which is what we have here. Now this is just the same as this. It's just 2 different notations, but I consider this a little more convenient. These, where are we going to get those? Well, we're going to come up here, and I meant to do that earlier, but we need to take the derivative of this and this. So dx dh is just going to be u1. This is constant. This is the constant coefficient to our input variable. So if we take the derivative with respect to h, that's just going to be u1. And the derivative dy dh is going to be u2. So dx dh is just this, dy dh is just this. And so now we're down to here, and you'll notice this is nothing more than the dot product of two vectors, this and this. So partial with respect to x, partial with respect to y, that is known as the gradient vector. And then this, of course, is just the direction vector. And there we go, we're done. So if you want to find a directional derivative, just take the gradient vector and dot it with the direction vector, and you're done.